Well, let's complete the section tonight. Number 51 gives us a special situation in the product rule. We know that the product rule for differentiation has two differentiable functions u and v. We are now considering that v is constant. V has a constant value c. Then what happens to the product rule? What does the product rule say in that situation? And then using that, can we conclude something about the constant multiple rule for differentiation, where we multiply a differentiable function by a constant, a real number? Let's see. By the product rule. So let's just write what the product rule is. U times dv dx plus v times du dx. Okay. Oh, and one more thing, we are writing this with the assumption that u is a differentiable function. That's why we say by the product rule. You need not again write that, okay, it's understood. And now we use the fact that v is constant, since v of x is constant. We have by the constant, I forgot the name of this rule. I think it's constant function rule or constant rule. The very first one, which tells us that when we differentiate a constant function, we get 0. Let me just simply write constant rule. This dv dx is 0. That means this term will vanish. We will have only this term. So is equal to v times du dx, or using the fact that v is constantly c, we can now write it in terms of c. And if you do so, you will write c in place of v, but we can change the order also. Instead of writing uc, we can write cu. So that will give me the derivative of cu. On the right hand side also, in place of v, we write c. And that is just nothing but the constant multiple rule. So you see that the constant multiple rule is a special case of the product rule, in the sense that it can be derived as a corollary of the product rule. Next, 52. So the solution ends there. It has a name also. The reciprocal rule. There are two parts. The reciprocal, let me simply write RR. Okay. the reciprocal rule says that at any point where the function v is differentiable and is different from 0 and is non-vanishing, differentiable and is different from 0, this is what we have. If you take the derivative of the reciprocal of v, that is why it has the name the reciprocal rule, that equals minus 1 over v square times the derivative of v with respect to x. That is the reciprocal rule. Now we have to show that the reciprocal rule is a special case of the quotient rule. Show that the reciprocal rule is a special case of the quotient rule, for which let me write QR. There is a part B also, but let us solve this one first and then we will see part B. Note that it is given that v is differentiable at some point x, and the constant function 1 is also differentiable at x. Constant function is differentiable everywhere, and in fact by the constant function rule or the constant rule, its derivative at any point is 0. So we can apply the quotient rule to the quotient of these two functions, the constant function 1 and v. And we already know what the quotient rule gives us. So let's just see ultimately in what form it comes out. So here I am writing the solution to part A only. By the quotient rule, straight away we apply the formula that the quotient rule gives us. So what does it tell us? It tells us first to write the square of the denominator, and then the denominator function is put here in the numerator and is multiplied by the derivative of the numerator minus. Then we write the numerator function and multiply it by the derivative of the denominator function. So this thing is 0 by the constant rule, minus dv dx divided by v square. So you can now clearly see that this becomes minus 1 over v square times dv dx. That's what we were claiming here. Now next see part B. Part B asks us to show that the reciprocal rule and the product rule together imply the quotient rule. show that the reciprocal rule and the product rule together imply, that's understood, the quotient rule. I'm not caring so much about grammar, okay, just what it means, that's what matters. So now we are going to assume that we have the reciprocal rule. Somehow we know the reciprocal rule and we know the product rule. Can we derive the quotient rule from them? Yes. Let U and V be differentiable functions. For this one, let's write the hypothesis. That is, we are going to write the hypothesis that we have in the quotient rule. Functions such that V of x is not equal to 0. Then, by the product rule and reciprocal rule, we have the following calculation. We want to know what the derivative of u over v is. We can write the quotient u over v also as u times the reciprocal of v. Now this is where at this step we apply the product rule. That gives me this plus 1 over v times du dx, and then to have this one we use the reciprocal rule. That gives us minus 1 over v square times dv dx, plus of course we have that other term du dx. And now what we can do, we can write the entire thing with a v square as denominator. That makes the first term, in place of the first term, we can now write minus u dv dx. And what happens here? Plus, we have a v square here, but already there was one v here in the denominator. So this term becomes v times du dx. And you just have to do a small interchange of position of the terms in the numerator. That is just v du dx minus u dv dx over v square. And this is precisely the quotient rule. This is the quotient rule. Next, 53. Another proof of the product rule. Sorry, not product rule, but power rule. Of the, we can no longer write PR. For positive integers. Here positive integer means that exponent that you have, x to the power n, that n we are talking about, that is a positive integer. I am not going to write entirely the thing. See, what the question asks us is this. It asks us to use this formula from algebra, which we already know. X minus c times x to the power n minus 1 plus x to the power n minus 2 times c, and so on, x times c to the power n minus 2 plus c to the n minus 1. This identity from algebra and this definition of derivative limit x tends to c, f of x minus f of c divided by x minus c. This is actually nothing different from the ordinary definition or the usual definition, which involves limit as h approaches 0. But it's just another way of writing that same thing. This also we have already seen. We have to use these two things to again derive this formula. Where n is a positive integer. Yeah. Let C be any real number. Let C belong to the set of real numbers. Then the derivative of f at C, how am I straight away writing this? I have to write what the function f is. Let f of x be equal to x to the power n, where n is a positive integer. And now I can write then the derivative of f at C by this definition of derivative is limit x approaching C of f of x minus f of C divided by x minus C. Now we use the definition of f. Then this limit becomes x to the power n minus c to the power n divided by x minus c. Obviously, when we consider a limit where the point where we are considering the limit is such that the variable approaches that point but is never equal to that point. And that is why division by x minus c makes sense. Since x is not equal to c, so x minus c is non-zero. And that's why by that identity that was suggested in the question, we will have x minus c times that other term. After cancellation, you can cancel because x minus c is non-zero. The function, this entire thing looks like this, plus x to the power n minus 2 times c, and so on, x times c to the power n minus 2 plus c to the power n minus 1. Note that this is a polynomial in x. And we already know that since any polynomial is continuous, so such a limit can be evaluated by simply substituting c for x, again by a previous theorem. C times c to the power n minus 2 plus c to the power n minus 1. And now we can clearly see that this is just a number of c to the power n minus 1s. But the question is how many? How many terms do we have in this sum, by the way? If you start counting from the second term here, that's because you can use the exponents of c in these terms to count the number of terms. Say this is your first term where your counting starts. You have 1 here. Then in the next term you will have x to the power n minus 3 times c square. That too indicates that this is the next term in your counting, second term. Like that, if you continue, by the time you reach this term, you would have counted n minus 1 terms. Combine that with that, this extra term, you have n number of terms. And that's why n number of c to the power n minus 1s are available here. Okay. So now you can write this for a general real number x. Here we did the entire thing for the real number c. At the real number c, we calculated the derivative. But of course, c is just any real number. So we can write hence f prime of c just means d dx of f at x equal to c. At x, that will look like this. For all real numbers x. Next, 54. Generalizing the power rule. We have we have the power rule for positive integer exponents and negative integer exponents, and of course for zero exponent, in which case the function becomes constantly 1. But so far we don't really know what happens when the exponent is a fraction. For example, we know this. We know, say, x to the power 100. We know what its derivative is. This is 100 times x to the power 99. Exponent is positive, is a positive integer. We also know this, minus 10. This derivative also, in form, it's exactly like this one. The exponent comes down and then gets reduced by 1. And even when the exponent is a fraction, a non-integral rational number, for this specific function also we have calculated the derivative, in fact many times, and it was found that its 1 divided by 2 times square root of x. But for a general fraction exponent, we don't really know. We haven't thought about it yet. Say x to the power 4 divided by 3. What do we do in that case? So this one is about that. In some steps, it will take us towards the answering this kind of things. The first part is this. Find the derivative of x to the power 3 over 2 by, it's also suggested how we have to approach the problem by writing this as x times x to the power 1 over 2 and applying the product rule. Now it makes sense how we can calculate this. We already know how to calculate the derivative of x, and this we already know, so we can apply the product rule here. And then there is more. Express your answer as a rational number times a rational power of x. When we say rational power, you have to understand that the power itself, the entire number is not rational. Rational power means the exponent is a rational number. Okay, and then there is one more line, work parts B and C by a similar method, because this is part A. Now before I clean this part, let's just see for a moment what this last portion tells us to do. We already know, for example, this is one such situation where the exponent is a rational number, and for this one we already know the derivative. But then the authors ask us to express your answer, for example this answer, as a rational number times a rational power of x. Let's do that for this one and see what we get. A rational number 1 over 2, which is 1 over 2 in this case, times x to the power minus 1 over 2. This is a rational power of x, where the exponent is this. Note one nice thing, that you can also write this as 1 over 2 minus 1. 1 over 2 minus 1 is minus 1 over 2. Now you look at the form of this result and recall what we just wrote moments ago. Again the form is same. Here the exponent is 1 over 2, that has come down, and then we have subtracted 1 from it. Here also the exponent is 100, that has come down, and we subtracted 1 from it. Is it going to be just like this? Let's see. In this one, however, that's not the function, but something else. This is interesting. The form, we are not losing the form. The form is same, only that the exponent has become fractional. So let's solve part A first, and then we will go to B and C. by the product rule ddx of x to the power 3 over 2, which of course is x times x to the power 1 over 2, but we will write that product in a more familiar form, x times root x, because this is how we encountered it before. So by the product rule, this is going to be x times ddx of square root of x plus square root of x times ddx of x, 1 divided by 2 times root x plus root x, because this is 1. Okay, now we have to do some simplification. All right. So what we can do, let me do on that side. If I write 2 root x as my denominator, then the first term in the numerator becomes x plus, and in place of this term we have 2 times root x times root x, that means 2x. So we are getting 3x divided by 2 root x, or 3 divided by 2 times, this is 1 and this is 1 over 2, the exponents. So by rules of exponents, we get this. 1 minus 1 over 2 is 1 over 2. However, note also that this is 3 over 2 minus 1. That's also 1 over 2. Again, the form is same. We are differentiating x to the power 3 over 2. That 3 over 2 exponent has come down, and then we subtracted 1 from it. Let's see what we have in part B. In part B, we have to calculate this x to the power 5 over 2. Again, by the product rule, we can write the given function like that product. Is it really this product? When you apply the rules of exponent here, you get 1 plus 3 over 2 as exponent, which is really 5 over 2. So by the product rule, x times ddx of x to the power 3 over 2 plus this times ddx of x. Now this we have already calculated here, and let's use this one. X times 3 over 2 times x to the power 1 over 2 plus x to the power 3 over 2 times 1. Now if you combine x and root x, you get x to the power 3 over 2. Now, after a little calculation, this becomes this, which can be written like this: 5 over 2 times 5 over 2 minus 1, because that is just 3 over 2. Again, that same form. The exponent has come down, and then we subtract 1 from it, and there is one more. By now, you are almost convinced that this is the general pattern, and it indeed is. Oh, I made a terrible mistake. Anyway, let me just show parts, then I will tell you what that mistake is. In my excitement to discuss about this pattern, I forgot that this is not 54. This is the last one, 55. Sorry about that. Okay. Before that, there is another exercise which we will do afterwards. This is exercise number 54. You can probably already see what we need to do here. 1 plus 5 over 2 is 7 over 2. So again, by the product rule, times d dx of x. This is available to us. So 5 over 2 times x to the power 3 over 2 plus x to the power 5 over 2 times 1. These two powers of x together give us x to the power 5 over 2. And just like that calculation, here 5 plus 2 becomes 7. So 7 over 2 times x to the power 5 over 2. And this is just x to the power 7 over 2 minus 1. And then there is a part D also. Part D asks us this. What patterns do you see in your answers to parts A, B and C? Yeah, that's the question. And there is one comment also. Rational powers are done in section 2.6. Okay, so when we see section 2.6, there we will prove the general version of this, where the function has exponent m divided by n, where m and n are integers and n is non-zero. The answers in parts A, B and C suggest that we should have this. Where m and n are integers, they belong to the set of integers, and n of course is non-zero. This is what, right now this is only a guess, but in section 2.6 we will prove it. And now let's go back to 54. Again I am repeating, this was not exercise 54, it was 55. 54 is generalizing the product rule. Oh, see, this is where I made the mistake. I actually started writing generalizing the product rule, but I mistakenly wrote generalizing the power rule, which is actually true because we are generalizing the power rule like this. But the beginning to question 55 is not exactly that. It writes rational powers. Okay, so that's where there was a mix-up. We already know what the product rule tells us. I am not going to write sentences again. The product rule tells us that if we have two differentiable functions u and v, then their product is also differentiable and the derivative of the product is just this, v times du dx. Now, what can we say about the product of three differentiable functions? Say we have three functions u, v and w. What about their product? We have, by the ordinary product rule, this. So we can treat this again as a product of two differentiable functions. How? One of them, say, is uv and the other one is w. Oh, and one more thing, how do we know that uv, that product, is differentiable? That comes from the ordinary product rule. You always keep in mind that the product rule not only gives us this equation, but behind this equation is the fact that it's also saying that uv is differentiable, and then it is saying that its derivative looks like this. So, by the product rule, we know that uv is differentiable. So this is a product, this is the product of two differentiable functions. One of them is uv and the other one is w. So we can apply the ordinary product rule here. Doing so gives us plus w times derivative of uv. uv times derivative of w plus w times, once more we can apply the product rule here, u dv dx plus v du dx. uv dw dx plus wu dv dx plus wv du dx. Now it looks quite somewhat complicated. Let us rearrange the terms to bring the sum in a form which will be easier to remember and interpret also. What we do, we first write this, and that too rearranging the individual terms here in that product. We write it as du dx vw, and then we write this one like this, u dv dx w, and finally we write the first one. So you can already see what the pattern is. You have three functions now, u, v and w. and say they are in this form. This is their product. The derivative, if I use the prime notation, it will become more clear. Looks like this. You again write the product UVW, but then you differentiate only U plus. Again you write the product UVW, but next you differentiate V plus. Then again you write the product and this time you differentiate W. So it's a sum of products again of all the functions, but one of them is the derivative instead of the ordinary function. That way. In fact, this is how the ordinary product rule also appears, because it looks like this now. U prime V plus U V prime. That's the pattern. In part B, the similar question is asked, but now for 4 functions. This pattern is only a guess right now. At this stage, having seen only 2 instances of this pattern, we cannot just straight away claim that this is going to be true in general. Let's see if that pattern persists here also with 4 functions. Four differentiable functions are given. I think it's better to actually use the prime notation. That way it will look very neat. Let me do that. It becomes somewhat cumbersome to keep writing dtx, u1, u2, u3, u4 prime. But again, how do we know that this product is differentiable? Well, you apply the ordinary product rule several times, or you apply the just now proved rule. It tells us that the product of 3 differentiable functions is differentiable. So by that, u1, u2, u3 is a differentiable function, a single differentiable function. And then you apply your ordinary product rule. By that rule, the product of this differentiable function and the differentiable function u4 is also differentiable. And that is why we can consider its derivative, the derivative of the entire product. Now, we can treat it as a product of 2 differentiable functions in another way also, which will be easier for us. And those 2 functions are these. One of them is u1, u2, and the other one is u3, u4. Now we apply the ordinary product rule. Well, actually, if you want, you can write it as u1, u2, u3 times u4 also. That way also you can do, because then you can apply this one. It's up to you what you want to do. By the ordinary product rule, u4 prime plus u1, u2 prime, u3, u4. And then once more we have to use the ordinary product rule. u1, u2 times u3 prime, u4 plus u3, u4 prime plus u1 prime, u2 plus u1, u2 prime times u3, u4. So let's do the multiplications first. u1, u2, u3 prime, u4 plus u1, u2, u3, u4 prime plus, then this one u1 prime u2 u3 u4 plus u1 u2 prime u3 u4. Now we can rearrange the things. First we would like to write this one, because here we have u1 prime plus, then the one with u2 prime u4 plus, then the one with u3 prime, and finally this one which has u4 prime. So yes, whatever we were suspecting in that previous part continues to be the case here as well. We differentiate one of the factors at a time and keep the others as they are. That's how we have the pattern. And now finally, can we say anything about the general case from here? Yes, we expect that the same thing is going to be true no matter how many functions are involved. So this will be part C. Here we have n number of differentiable functions where n is finite, of course, n is a positive integer and n is at least 2. Our claim is this: we claim this, that not only is the product differentiable, but its derivative is going to look like this. Because a general sum is involved, it's better to use the summation notation. u1, u2, ui minus 1, ui prime, ui plus 1, un. So this is a sum where the general term is going to look like this, and the ith term has the derivative of the ith function. The others are same. For example, here the first term has u1 prime, the second one has u2 prime. So just like that, here the ith one has ui prime and the others are same. But this is again only a claim. You have to prove this claim now. And this is where we are going to use mathematical induction. The case n equal to 2 is just the product rule. It's nothing else. Okay, so there you do not have to do anything. We have already done that. And this is the basis for our induction. Suppose the claim is true for some integer n which is at least 2. Okay, now let w1, w2, wn, wn plus 1 be differentiable functions. Okay. Then let me straight away just simply consider their product, and in fact not just that, the derivative of the product. Behind this there is that thing which we are not mentioning explicitly, namely the fact that first of all, you can consider this product and its derivative because this product is differentiable. Again, how? Same technique, same logic. By the induction hypothesis, the claim is true for a product of n number of differentiable functions. Hence, the first part of the product, which involves these first n functions, is a differentiable function by our induction hypothesis, by the supposition that the claim is true for n. And wn plus 1 is already differentiable. So we are now looking at the product of two differentiable functions. The first of them is this product involving n functions, and the other one is wn plus 1. So by the ordinary product rule, their product is differentiable, and that is why we can consider this derivative in the first place. Alright. And at this very next step, in fact, we are going to apply the ordinary product rule with this as one function and this one as another function. By that, we have this wn plus 1 plus wn times wn plus 1 prime. Now, in place of this derivative, we can write a sum like this one. But why? Because we have supposed that the claim is true for n. That is why, by the induction hypothesis. Okay, so what will that sum be? That sum will look like this. Summation w1, w2, wi minus 1, wi prime, wi plus 1, then wn, where I varies from 1 to n, but do not forget that this entire thing is multiplied by wn plus 1 plus this other term. Now you can, of course, because this is a sum and we are multiplying the sum by from outside by another thing, you can multiply each term of the sum by that thing. w1, w2, I minus 1, wi prime, wi plus 1, wn plus 1. Here I varies from 1 to n plus so if you now include this extra term to this sum, then the sum changes. Do you see what type of terms the sum has? Here again we have a product of all the functions, but one of them is replaced by its derivative in each term. And the derivative actually happens, or the differentiation happens to each of the first n functions. But wn plus 1, the derivative of that does not appear in this sum, but it appears in that extra term. So if I now write another sum in place of this, will it make sense? Let's see. wi minus 1, wi prime, wi plus 1, wn plus 1, but this time we let I vary from 1 to n plus 1. As I varies from 1 to n, you get the terms of this sum. and when I is n plus 1, you get this term. So yes, they are the same thing. But this is precisely what we were claiming if in place of n functions you have n plus 1 functions. So this completes the induction and our claim has been proved. And proves our claim. From now on, we can use this formula. The formula, although it looks very complicated in this form, but the basic idea is just simple. You write the product of all the functions. Every time you write a new term, but then differentiate one of them at a time. And that's how your sum goes. So if we use this formula directly, we won't have to go through the process of applying the product rule again and again. Okay, so that's what we are going to remember, and we will use it freely without any further comment. And this also completes this section. After this, there is one, the next section is about rates of change. So far, we already know that derivatives are rates of change. But so far, the applications of this idea have been to geometric situations where we calculate tangent lines. Those things have been our focus so far. But in the next section, we are going to heavily focus on this rate of change aspect of derivatives, and we are going to see many applications. So we will see that, and tomorrow, as usual, we have our linear algebra. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.